Imagine hitting an invisible wall, a sudden explosive punch that rattles everything for miles around. That's what happens when a fighter jet breaks the sound barrier. But here is the main question. If sound is already traveling at its maximum speed, how can anything possibly break it? Is it actually dangerous? Could that massive boom shatter windows or even hurt someone? Let's find out. The invisible wall. What is the sound barrier? To understand how a jet breaks the sound barrier, we have to start with what the barrier actually is. It sounds complicated, but we can simplify it quickly. The term sound barrier is really just a name for a specific speed, Mach 1. Mach 1 is the speed of sound, which is about 767 miles per hour at sea level. Now, why is Mach 1 so important? Why is it a barrier in the first place? To picture it, think about what sound is. Sound is basically vibrations or tiny waves of pressure moving through the air. When I talk, the air particles near my mouth bump into the particles next to them, and that wave of pressure travels to your ear. Now imagine a fighter jet cruising along. As the jet moves, it's constantly creating its own sound waves, like ripples in a pond. These ripples or pressure waves move away from the aircraft in all directions at the speed of sound. They are warning the air in front of the jet that the plane is coming. If the jet is moving slowly, say at 300 miles per hour, its pressure waves zip ahead easily. The air in front has plenty of time to get out of the way, and the flow of air around the wings is smooth, no problem. But here is where things get interesting. What happens when the jet speeds up? As the jet approaches Mach 1, say 700 miles per hour, it starts catching up to its own sound waves. It's like a boat trying to outrun its own wake, but in the air. The sound waves ahead of the jet don't have time to fully disperse. Instead of warning the air that the jet is coming, they start to pile up right in front of the aircraft. They are essentially stacking up one on top of the other, forming a wall of intense, compressed air. This piling up of air is what pilots and engineers call compressibility. Imagine you're running toward a crowded subway door. If you run slowly, people step aside. But if you sprint as fast as they can move, they stack up right in front of the door, and suddenly you hit a massive crowd. That crowd is the sound barrier. This pressure buildup causes serious trouble for the plane. The airflow over the wings goes wild, and the plane starts shaking violently. This intense shaking is called buffeting, and for decades this buffeting was so extreme that engineers feared the plane would simply tear itself apart. That's why we called it a barrier. The first planes that tried to go this fast failed completely. They hit the wall, lost control, and sometimes the wings ripped off. This was the problem. How do you punch through a wall of compressed air without breaking the plane? The immediate solution required changing the shape of the plane, making it pointed and sleek, like a needle. But the real mystery isn't hitting the wall, it's what happens after you punch through it. And that's what we're going to discuss next. The biggest payoff of this entire experience is the moment the jet crosses that invisible line and the pressure is suddenly released. But before we get there, you might be thinking, if that wall of compressed air is so scary, why aren't all jets trying to fly through it? Why do we see jets moving slowly sometimes? The reason lies in the massive amounts of energy required to achieve Mach 1. You see, once you are moving close to the speed of sound, the drag, the resistance of the air pushing back, increases exponentially. You need incredible power just to maintain speed, let alone increase it. This is why fighter jets use afterburners. An afterburner is essentially dumping extra fuel into the engine exhaust nozzle and lighting it on fire. It provides a massive temporary thrust boost, but it drinks fuel at an alarming rate. The whole point of this entire process is to build up enough kinetic energy and thrust to overcome that intense drag just before Mach 1. It's like climbing a very steep hill. You need all your power right at the top, or you stall. So, to summarize this first point, the sound barrier isn't a physical wall, but a point where the jet catches up to its own pressure waves, causing intense drag and dangerous buffeting. Overcoming it requires massive thrust and a sleek design. Okay, we've covered the invisible wall itself. Now let's get to the fun part, the main payoff. What happens the moment that compressed air is released, and how does that create the massive sonic boom we hear on the ground? The sound cannon. Understanding the sonic boom. If a jet is traveling below the speed of sound, let's say 600 miles per hour, the air pressure waves spread out in front of it. The sound travels faster than the jet, so the sound you hear comes before the plane arrives. But the instant the jet hits 767 miles per hour, Mach 1, it overtakes all those piled up pressure waves we just talked about. When the jet passes Mach 1, it's not just catching up to its sound, it's leaving its sound behind. All that previously compressed air is suddenly shocked and stretched out, and this release forms what is known as a shock wave. Think of it like snapping a towel. When you snap it quickly, you hear a loud crack. That crack isn't the towel hitting the air, it's the tip of the towel moving so fast that it creates a small, localized sonic boom right there. Now imagine that snap traveling with the jet. The shockwave isn't just one boom, it's a continuous cone of high pressure that trails behind the aircraft for the entire time it is moving faster than sound. Picture a powerboat moving quickly through water. The water cannot get out of the way fast enough, so it creates a V-shaped wake that trails behind the boat. That wake is the boat's shockwave, and it carries the boat's energy. A jet moving at Mach 1 creates the exact same thing, but in 3 dimensions. A gigantic cone of pressurized air. This is called the mach cone. The aircraft is sitting at the point of the cone, moving ahead of the noise it creates. Now, for people on the ground, what does this mean? Since the cone is continuous, it sweeps across the ground along the jet's flight path. If you are standing directly in the jet's path, the pressure change you feel isn't just one single blast. It's 2 incredibly sharp pressure spikes, one from the nose of the plane and a second, sometimes slightly weaker one, from the tail. When these 2 pressure spikes hit your ear, they happen milliseconds apart. Your brain interprets this sudden, violent change in air pressure as a single, massive explosion, the sonic boom. It's often described as a loud clap of thunder, a cannon shot, or even a low, rolling rumble, depending on the jet's altitude and size. And here's a common misconception. People often think the jet makes the boom only when it crosses Mach 1. Wrong. The jet makes the boom the entire time it flies faster than sound. If a jet flies supersonic for 5 minutes over a straight path, the Mach cone trails behind it for that entire 5 minutes, creating a 5-mile-long path of continuous shockwave on the ground. Anyone standing along that 5-mile-long path hears the boom as the cone passes them. So, if you hear a sonic boom, it means the jet was moving faster than sound at that moment, but it also means the jet is already long gone. You heard the past. This is why the boom is such a physical, visceral thing. It's a literal punch in the chest from the atmosphere. The pressure changes can be strong enough to rattle windows and, in some cases, cause damage. Which brings us to the serious side of going supersonic. You see, once we understood the physics of the boom, we had to deal with the consequences. The stakes. When supersonic flight gets dangerous for the pilots and the people on the ground, breaking the sound barrier isn't without serious risks and engineering challenges. For the pilot in the cockpit, the process of going supersonic is surprisingly smooth. Once they push past Mach 1, the terrifying buffeting and shaking suddenly stop, and the flight becomes incredibly calm. They are now moving faster than the air disturbance they create. However, the real danger for the pilot isn't the boom itself, but the massive forces acting on the aircraft at that speed. We're talking about G-forces. G-forces are the measure of acceleration. When a pilot turns a jet sharply at 1,000 miles per hour, the forces pushing them into their seat or trying to rip their head off are immense. If a pilot executes a hard turn, they might pull 9 Gs. That means their body feels 9 times heavier than normal. At 9 Gs, a pilot struggles to keep blood flowing to their brain. They risk temporary loss of vision, known as GLOC, G-force-induced loss of consciousness. This is why pilots wear special pressurized suits and rely on advanced technology just to stay awake and functional. The sheer speed requires constant alertness because reaction time shrinks to nothing. Now, for people and structures on the ground, the danger is different. The massive energy released by the shockwave. The force of a sonic boom is measured in pounds per square foot, CPSF. A quiet, everyday sonic boom might be 1 to 2 PSF. But if a large jet, like a bomber, breaks the sound barrier at low altitude, the pressure can easily hit 10 or 15 PSF. During early supersonic testing in the 1960s, the US government ran experiments to measure the effects of the boom. The results were dramatic. In some communities, the relentless sonic booms shattered windows, cracked plaster, and damaged fragile structures. People complained constantly about the noise, which often startled livestock and disrupted daily life. Imagine living next to a military base where a cannon fires unpredictably 20 times a day. That was the reality. This environmental and public relations disaster led to a major change. The US and many other nations eventually banned routine supersonic flight over land. This is why you rarely hear fighter jets dropping booms unless they are far out over the ocean or in designated testing zones. But here's the interesting paradox. The very machines that cause this massive, disruptive boom require incredible precision to build. The pressure change from the boom means the aircraft structure itself must be flawless. Historically, companies that lost focus on that core engineering quality often failed spectacularly. Think about the cautionary tale of White Motor Company. They were known for building some of America's toughest machines, like reliable trucks used in World War II. Their engineers were obsessed with quality and durability. But then, corporate executives got greedy and decided to chase growth through endless acquisitions, buying companies making agricultural tractors and huge mining equipment. They stretched their resources too thin, trying to compete in too many different fields at once. The original engineering culture that demanded precision was diluted by financial pressures. They kept trying to cut corners. And guess what happened? Quality problems emerged. Warranty claims increased. Eventually, debt soared and the whole empire collapsed. The lesson here is simple. Whether you're building a commercial semi-truck or a Mach 2 fighter jet, if you compromise on the engineering details, if you let greed replace precision, the machine fails. In the case of a supersonic jet, that failure is instant and catastrophic. To withstand the violent shockwave and the stresses of supersonic travel, the jet requires materials and construction that are perfect. Every rivet, every joint, every wing surface must be engineered to handle the immense changes in temperature and pressure. The fact that pilots can fly routinely at Mach 2 or Mach 3 is a testament to the fact that those aerospace engineers refused to compromise on precision. It really makes you wonder, how did we even prove this was possible? It took a bold plan and a pilot with nerves of steel. The breakthrough. The pilot. Who broke the barrier? For centuries, scientists assumed that flying faster than sound was simply impossible. The violent shaking planes experienced near Mach 1 seemed to confirm that belief. It was considered the ultimate speed limit for aircraft. Then came World War II. The war forced rapid development in aviation, especially in jet and rocket technology. After the war ended, the race to break the sound barrier officially began. The US military knew they needed a special aircraft. One designed from the ground up to handle the intense stresses of Mach 1. They didn't use a normal jet, they built a rocket plane, designed just for this single purpose. This is the story of the Bell X-1, painted bright orange, and its pilot, Chuck Yeager. Somebody wanted to prove that humanity could fly faster than sound, but existing propeller planes would tear themselves apart when they hit the pressure wall at Mach 1, and the flight was incredibly dangerous. So then the military built the rocket-powered Bell X-1 and they hired a brave, experienced test pilot named Chuck Yeager. Yeager's first flights were terrifying. As he approached the speed of sound, the buffeting was so intense he struggled to control the aircraft. It felt like hitting a brick wall in the air. Many people involved in the project feared he would die trying. The official attempt happened on October 14th, 1947. The Bell X-1 wasn't launched from the ground. It was carried high into the sky underneath a B-29 bomber, acting like a giant cradle. When the B-29 reached altitude, Yeager dropped the X-1 and immediately ignited the rocket engine. Yeager pushed the plane faster and faster. The violent air pressure resistance, the barrier, built up exactly as expected. The stick forces needed to control the plane became nearly impossible to manage, but Yeager kept pushing. At exactly 10:18 a.m. high over the Mojave Desert, the instruments inside the cockpit changed. Yeager later reported that at 0.94 Mach, the plane began shaking severely. But then, At 1.05 Mach, the shaking instantly stopped. It was suddenly smooth and quiet, like riding a glass-smooth surface. He had punched through the invisible wall. The ground crew below heard a massive, sudden double clap, the first controlled sonic boom in history. Jaeger was now moving faster than the sound he created. When he landed, the team found that the supersonic air movement had been so forceful that it had ripped rivets off the outer skin of the X-1. The machine barely held together, but it worked. This moment changed everything. Jaeger didn't just break a speed record, he proved that the barrier was not a solid, unbreakable wall, but simply an intense pressure that could be overcome with the right power and shape. This breakthrough started the era of modern flight. Immediately, engineers focused on building commercial airliners like the Concorde and military jets that could fly routinely at Mach 2 or higher. The story of the jet age, of global travel and high-speed defense, all starts with that moment of quiet smoothness after the massive initial boom. Why precision matters, the engine of speed. But let's pause and think about the power needed for this feat. Jaeger needed rockets, but modern jets use specialized turbine engines. Achieving supersonic speed demands an engine that is both incredibly powerful and surprisingly precise. It can't fail when faced with the extreme temperatures and pressures of Mach 1. This focus on reliable, perfect engines reminds us of the history of Detroit Diesel. Detroit Diesel built their name by creating engines that were practically indestructible. Their Series 71 two-stroke engines powered Allied tanks and landing craft during World War II. They were designed to be simple enough to repair in the field with basic tools, and they could tolerate massive abuse. They were pure mechanical artistry. But as environmental and market demands changed, especially regarding emissions and noise, Detroit Diesel had to adapt. Their famous screaming Jimmy engines, while beloved by enthusiasts, were too loud and too dirty for the modern world. In 1987, they made a massive switch. They introduced the Series 60, their first four-stroke engine, controlled entirely by electronics. This engine was a huge success because it proved they could maintain their reputation for reliability while meeting the new demands for efficiency and cleanliness. The point here is that speed and power must be matched by reliability. An unreliable engine, no matter how fast it is useless. We saw this exact problem play out with the collapse of the MaxxForce engine line in the early 2000s. Navistar, the company behind MaxxForce, made a risky bet. They tried to meet new, strict emission standards by using a technology called advanced EGR, exhaust gas recirculation. They recirculated massive amounts of hot exhaust gas back into the engine itself, arguing that this was elegant engineering because it avoided the extra tanks and fluids used by competitors. They were convinced they had a simpler solution, but they pushed the technology beyond its practical limits. The engine components, like the EGR coolers and turbochargers, were subjected to extreme, crushing temperatures, well over 1,000 degrees Fahrenheit. The resulting heat stress caused cracks, failures, and massive repair bills for truck fleets. Navistar thought they could compromise on the core principle of thermal management to achieve regulatory compliance. They tried to rush their product to market with inadequate testing. The market quickly showed them they were wrong. The engines broke down constantly, warranty claims exploded, and the company eventually had to scrap the entire MaxxForce program and admit defeat. The cost was staggering. Why bring this up? Because supersonic flight is an engineering problem on steroids. It is a constant battle between speed and structural integrity. If the metal alloy in the jet's engine is stressed 1 degree too high, if the design is compromised just slightly to save a few dollars, the plane falls apart or the mission fails. The very best aviation successes, whether the Concorde or the F-22 Raptor, are built on the foundation of engineering that refuses to accept shortcuts. They understood that success in speed relies entirely on maximum durability. The future of speed and the hidden boom. So we started with the massive, unexpected boom, and we've learned that it's just the physical consequence of a jet moving faster than its own pressure waves, creating a continuous Mach cone. We also know that modern flight is only possible because of dedicated, uncompromising engineers. But what is the future of supersonic flight? Since routine supersonic flights were banned over land, engineers have been trying to solve one single question. Can we eliminate the sonic boom? If we could somehow reshape the shock wave, flatten the sharp pressure spikes, the noise wouldn't be a jarring, cannon-like explosion. Instead, it might be a low, muffled thud, or perhaps even silent. NASA has spent years developing experimental aircraft specifically designed to test this idea. Their current project, the X-59 Quiet Supersonic Technology, QuSST aircraft, is built with a radical, extremely long and needle-like nose. The goal of this unique shape is to control exactly how the air compresses and releases the shockwave. Instead of two massive pressure spikes hitting the ground at once, creating the boom, the X-59 aims to stretch those pressure changes out over a longer time. If they succeed, the future of air travel could see commercial flights routinely crossing the US in half the time. You could fly from New York to London in under 3 hours and nobody on the ground would hear a thing. This process, the incredible pressure, the sudden quiet and the trailing explosion, is what happens when a fighter jet breaks the sound barrier. It is a feat of power, physics and patience, proven by a brave pilot in a dangerous time.